In 1638, near the end of his life, Galileo published his Discorsi, Two New Sciences. It was the book where he laid out what he had learned about motion, strength of materials, and the physics of the world around him. In the fourth day of the dialogue, Galileo discussed the shape of a hanging chain. His instructions were simple: drive 2 nails into a wall, hang a light chain between them, let it sag under its own weight, and the curve you get, he said, is a parabola. It was a confident claim. Galileo had spent decades pulling the parabola out of every physical problem he touched. The path of a cannonball in flight, the cross-section of a loaded beam, the shape of water in a rotating bucket. The parabola kept showing up everywhere he looked. So of course the hanging chain, arching gently between 2 nails, must also be a parabola. For the next 30 years, nobody serious argued with him. If you wanted to draw a parabola in 1650, you drove 2 nails into a wall and hung a chain. You put a sheet of paper behind it. You traced the curve. That was the method. Except the chain is not a parabola. Galileo was wrong. The real curve obeys a different equation, comes from a different family of functions, and requires a whole branch of calculus that had not yet been invented. This is the story of how, over almost 100 years, people figured out the difference. It involves a mostly forgotten German polymath who measured carefully when no one else bothered, a public mathematical challenge printed in Leipzig, and 3 of the best minds in Europe sending sealed solutions through the post in 1691. Before we get into who was right and who was wrong, let me explain why Galileo's mistake was a reasonable one. The hanging chain curve and the parabola are not just similar. Near the bottom of the sag, they are nearly identical. If you hang a chain and draw the best-fitting parabola behind it, the 2 curves stay within a hair's breadth of each other for most of the visible arc. You could put them on top of each other and not tell them apart. The reason is this: any smooth curve, near its minimum, looks like a parabola. That is one of the most basic truths in calculus. Take the function that describes the chain, expand it around the lowest point, and the first thing that appears is a quadratic term, then a 4th power term, then a 6th power term, and so on. The difference between the chain and a parabola is hidden in that 4th power of the horizontal distance. For a shallow sag where the horizontal distance is small, the 4th power is tiny. It is smaller than the thickness of the line you draw. So when Galileo looked at a hanging chain and compared it to a parabola, the 2 matched, not in some loose hand-waving sense. Measurably, experimentally, within the precision of a 17th century draftsman, the 2 curves were indistinguishable. In a later, quieter passage, Galileo himself backed off slightly. He noted that the match between the chain and a parabola is, in his words, only approximate. It holds best when the chain is nearly flat. When the sag gets deep and the slope at the edges grows larger, the 2 curves begin to pull apart. But with a shallow chain on a drafting table, the difference is invisible. Galileo could not see it. Nobody with a 17th century workshop could have seen it. And so for 30 years, the parabola was the answer that everyone accepted. The first person to find the crack in Galileo's claim was not famous. His name was Joachim Jungius, a German polymath, mostly forgotten now, who spent his life moving between medicine, logic, botany, and mathematics. He died in 1657. His notebooks sat unpublished for over a decade after his death. In 1669, his former students finally got his mathematical work to the printer. Buried in the papers was a careful experimental study of the hanging chain. Jungius had done what almost nobody else had bothered to do. He had measured. He hung chains from pairs of nails. He drew parabolas behind them that matched the endpoints in the lowest point of the sag, and he checked inch by inch whether the rest of the chain lay on the parabola. It did not. Near the edges of the curve, the chain consistently sat slightly outside the parabola. Not by much, but always outside. Always in the same direction. Always in a pattern that could not be explained as measurement error or accident. So Jungius had proved the negative. The hanging chain is not a parabola, but he had not found the positive. He could not say what the curve actually was. He had the shape in front of him in the form of real chains hanging off his drawing board. He could describe where it departed from the parabola, but he had no equation for it. Nobody did. The tools to write that equation had not yet been invented. Jungius published the disproof and died 20 years before the real answer appeared. For 2 more decades, the problem sat open. The most serious physicists and mathematicians in Europe knew that Galileo was wrong and knew that nobody knew what was right. The chain, hanging quietly in a workshop somewhere, kept its secret. In May of 1690, Jacob Bernoulli published a problem in the journal Acta Eruditorum. The journal was based in Leipzig. It was the main place where natural philosophers and mathematicians across Europe read each other's work. Jacob's challenge was a direct one. Find the shape, he wrote, of a loose string hung freely between 2 fixed points. This was not an innocent question. Jacob Bernoulli was a major figure. He was the older of the 2 Bernoulli brothers, a pioneer of what we now call probability theory, and a bright and competitive man. He had tried to solve the hanging chain problem himself. He had failed, and in a move that was not uncommon in the 17th century, he took his failure and turned it into a public challenge. If I cannot solve this, he was essentially saying, let us see who can. The responses came fast. By the end of 1690, Christian Huygens in Holland had solved it. Huygens was 61 years old. He used the classical, geometric tools he had learned as a young man, before calculus existed. In Germany, Gottfried Leibniz solved it too, using his own freshly invented differential calculus. It was one of the first real demonstrations that the new calculus could settle old open problems. And from Switzerland, Johann Bernoulli, Jacob's own younger brother, sent in the third solution. Johann, who was in his early 20s at the time, and who would spend the rest of his life making sure everyone knew that he had solved what his older brother could not. All three solutions were published together in the June 1691 issue of Acta Eruditorum. In a letter to Leibniz the previous autumn, Huygens had proposed a name for the curve. He took it from the Latin catena, meaning chain. The curve, he wrote, should be called the catenary. So what is the curve actually doing? Why is it not a parabola? Here is the key insight that all three solvers found, in their own ways. It comes down to where the weight of the chain lives. Imagine a chain hanging between 2 points. Now zoom in on a tiny piece of it. A short segment somewhere along the curve. Call its length the arc length ds. That little segment is acted on by three forces. At its left end, the rest of the chain pulls on it along the tangent direction. Call that tension T on the left. At its right end, the chain pulls on it the other way, also along the tangent, but along a slightly different direction because the curve bends between them. Call that T on the right. And gravity pulls the segment straight down. The force of gravity is proportional to the mass of the segment, which is proportional to the arc length ds. Here is the pivotal fact. The weight of the segment is proportional to its arc length, not to its horizontal extent. This single sentence is the whole difference between the catenary and the parabola. For the chain to hang in equilibrium, these three forces have to cancel out. Horizontally, tension pulling right at the right end must match tension pulling left at the left end. That means the horizontal component of the tension stays constant along the entire chain. Every segment, no matter where you look along the sag, carries the same horizontal pull. Vertically, the change in tension across the segment has to match gravity pulling it down. The vertical component of the tension climbs as you move outward from the bottom of the chain, and it climbs by exactly the weight of the chain below it. That weight is proportional to arc length. This is the load on the chain. It is distributed along the length of the rope, not along the horizontal axis. That one sentence is what separates the catenary from the parabola, and every step of the coming derivation flows from it. Now we turn the physics into an equation. The slope of the chain at any point is the ratio of vertical tension to horizontal tension. Vertical over horizontal. If we write the chain as y equals y of x, the slope is y prime. The vertical tension at a point equals the weight of arc below that point divided by the constant horizontal tension. That gives an equation for y prime. Differentiate it and you get an equation for y double prime, the curvature of the chain. After some algebra, which the three solvers all worked through in slightly different ways, the equation comes out clean. Y double prime equals 1 over a times the square root of 1 plus y prime squared. Here a is a constant with units of length, built out of the tension and the weight per unit length. Now look at that square root, 1 plus y prime squared. That is exactly the arc length formula, and it is exactly the form that the hyperbolic functions were born to handle. Try the substitution. Let y prime equal the hyperbolic sine of some new function u of x. Then 1 plus y prime squared becomes 1 plus sin squared u, which by a standard identity equals cosh squared u. The square root becomes cosh u. The equation collapses. The cosh on the right balances the cosh hidden in the derivative on the left. What remains is u prime equals 1 over a. Integrate that and you get u equals x over a. So y prime equals sin of x over a. Integrate once more. Y equals a cosh of x over a. That is the catenary. The curve everyone had been chasing for a century is a hyperbolic cosine, a function that in 1691 was barely a decade old. Huygens, Leibniz, and Johann Bernoulli had all arrived at the same answer by 3 different routes using 3 different sets of tools, published in the same journal in the same issue. Here is where the story takes a turn that most people miss. Once you understand the catenary, you might assume that every chain-like curve you see in the real world is a catenary, power lines strung between poles, chains on a ship, ropes hanging from a beam, and mostly yes, a rope hanging under its own weight, with nothing else pulling on it, makes a catenary. But look at a suspension bridge. Look at the Golden Gate, the Brooklyn Bridge, the Verrazano Narrows. The main cables of those bridges make a long, elegant curve between the towers. That curve is not a catenary, it is a parabola. Here is why. On a suspension bridge, the main cable is not hanging under its own weight. It is supporting the road deck below. The deck is enormous. Steel, concrete, cars, people. The weight of the deck is so much bigger than the weight of the cable that the cable's own mass is essentially negligible. You can ignore it. And the deck has a very specific property. It is laid out along the horizontal. The weight of the deck per unit horizontal distance is constant. Every meter along the x-axis carries the same mass of deck. Not every meter along the cable's arc. Every meter along the ground. So the equations change. The load is no longer proportional to arc length. It is proportional to horizontal distance. The force balance still holds, but one factor of square root of 1 plus y prime squared disappears. What replaces it is a plain constant. The equation becomes y double prime equals a constant that integrates to a parabola, plane x squared over 2a. Galileo was right, for the wrong reason. He had seen a parabola hiding in the shape of a chain, and he was wrong about why it was there. But once people started building suspension bridges, 200 years later, the parabola showed up again, for the right reason. Change the load, change the answer. The world holds both curves at once. There is one more chapter. In 1675, 15 years before Jacob Bernoulli posed the catenary challenge, Robert Hooke wrote down a principle in one of his notebooks. He wrote it as an anagram, a letter cipher, so he could claim priority later without revealing the idea to his rivals. It was decoded after his death. Translated from the Latin, it reads, "As hangs the flexible line, so but inverted will stand the rigid arch." Hooke had seen something the ancient builders had not written down. If you take the shape of a hanging chain, the curve that forms under pure tension, and you flip it upside down, you get the shape of a perfect arch. A curve that stands under pure compression, no bending, no side forces. The stone or brick simply pushes along the curve from one end to the other, and the structure holds itself up without effort. The catenary is the shape of effortless support in both directions. Hang it, it holds itself together in tension. Flip it, it holds itself up in compressions. Every other shape you try will require the arch to resist some bending force somewhere. The catenary alone among curves does not. This is why arches, good arches, have so often ended up close to the catenary shape, and why the most famous inverted catenary in the world stands in St. Louis, Missouri. The gateway arch is not quite a plain catenary, it is a weighted catenary. The cross-section of the arch tapers as it rises, wider at the base, narrower at the top. That variable thickness changes the math slightly. The equation becomes y equals b cosh of x over a, with two different constants instead of one. The actual equation carved into the design is y equals 68.8 times cosh of 0.01x. In feet, in centered coordinates. The peak sits 630 feet above the ground. 3 centuries after Jungius first wrote in the margin that the chain is not a parabola, the catenary is everywhere. It holds up necklaces and power lines and ship chains and the seat of a hammock. It holds up the gateway arch, standing in pure compression, a hanging chain flipped upside down and turned to stone. And it took a 61-year-old Huygens, a 44-year-old Leibniz, and a 23-year-old Johann Bernoulli racing each other through the spring of 1691 to find the equation hiding inside.